This is the picospin 45 MHz NMR spectrometer. This is our instrument, and this is the number refers to the instrument ID, and it's linked to the server. It's a very simple instrument, and the magnet is a fixed magnet, and the magnetic field is just 45 MHz. It's a low field fixed magnet. And we are going to introduce the sample in here. It's an inlet port, the liquid sample, and then it's going to come out in here. That's the outlet port. So there's a loop, and it accommodates 20 microliters of the sample. And now I'm going to prepare the sample. So the sample for experiment 2, I labeled this as a number. So for the unknowns, it's going to be labeled as either 1, 2, 3, 4, or letter A, B, C, D, and so forth. So this is labeled as 2, so we're going to be working on 2 as a demonstration. So this is a syringe. It accommodates about 0.5 ml, so it's 500 microliters. And I'm going to withdraw like halfway. It's about 300 or so microliters. So I will immerse the needle and then withdraw like halfway. And I cap it. So the instrument is under the hood. So I tap it so that the bubbles go up. And then I'm going to use this paper towel to make sure that that part doesn't have any air. And now I'm going to introduce the sample into the inlet port. So this is the inlet port. So I'm going to watch the outlet port that it drips about 8 drops or so that I know that whatever sample is inside, I push it out. And I'm just introducing my sample. So it's a very tiny Teflon. So now I have the needle inside the Teflon, so I'm going to slowly inject. And again, watching the outlet port over here, that it's dripping about 8 drops or so. So 1, 2, and also watching this part that it's not dripping or leaking. 3. Okay? So our sample is inside. So I still have a lot, by the way. So I'm just going to cap it in case I need to inject more. So we're now ready to run the sample, and so it's connected to a server. So I'm just actually on Google. So we are now going to run the NMR spectrometer. This computer is linked to the instrument, the picospin. And now we are going to access the software. So on the task bar in here, you're going to just write picospin. And then it's already in here because I used it already. So this is the instrument ID 163.245.19.69. And you just click on it. And it now goes to the thermoscientific server, and then it would tell you the picospin 45, which is the instrument, and this is called the thermoscientific software server that would run the instrument. If you're going to run from the beginning, and then if there's already a file, you can just click on the files, and then so you click on it. So from the file, you can select a previous run. So for example, I'm going to do test run. So I'll click on it, and then it will load the setting. So now I'm going to do use the settings at run. So in this window, you have the frequency of the instrument, which is indicated as 45.160389 megahertz or 45 megahertz. So this is the frequency of the instrument. And then, so the important parameter here that you need to look at is the number of scans. So I typically do 8 scans, but you can do more, but it's increment up to the end. So this one is 2 to the third, 8, or you can do 16, you can do 32. And then the more scans you have, the better would be the signal to noise ratio. So those are the things that you need to worry about. The others are default settings. So now I'm gonna type in the name of my sample, and I'm gonna do unknown 2 or whatever name you want. So it's arbitrary, but for this one I'm gonna do unknown 2 as my sample. I will now click start run. So we're now ready to start scanning. So there are 2 parts to collect the data for the NMR. The first part is to acquire. So that's the acquisition portion. And then the next part is to process the data or the processing. So I will now click start run. So it would scan from 1 to 8 and then it will stop at 8 scans. So start run, and then if you look at the bottom, it's ready to start scanning. So scan number 1 until 8. So this is now the raw data, and it's in milliseconds. So this is the time domain, and it sort of processes it, but it's raw. So it's not a very good spectrum yet. But this is basically the frequency domain. But it's a raw processing. But we're gonna process it differently once it stops acquiring the data. So right now it's 7 scans, and then 1 more scan left. And now it said script 1 pulse completed successfully. That's actually 8 scans. So if you look, there are 8 scans. And now the next part is, again, the top screen shows you the raw data. And now I'm gonna do download data. So that would transfer the data to a different software we are now going to process. So download data. And then at the bottom, I will now click on it. It goes to a different software. So it's a processor. And now this is the raw data. We are now ready to process. So first, the icons are on top. And then I'm going to do what is called zero filling. And then I will change this to 16,000 by using the top arrow. And all of these steps are actually in a manual. So if you're running this, we have a manual to follow the instructions. And then W functions, this is called what is referred to as line broadening. This is mainly to process the data and make the spectrum better so that it will have a large signal to noise ratio. So the next step is to process the data from the time domain, time, to a frequency in the X scale. So I'm now going to do processing, which is here. So it transforms that to a Fourier transform, complex transform, and now I have the data in here. But I will do more processing, and then I will now do what is called phasing. And now I can make the baseline better. So I can also do more phasing. And now I can expand. So this is now our data. This is now in chemical shift ppm. So now I'm doing referencing. I'm now doing referencing, and I will reference it to, there's a solvent that I can use in here. So this is basically the aliphatic portion, and I will set it, it's kind of similar to the peak in ethanol, so I will set that as 1.1 ppm, and then everything else will move and calibrated. So now I'm ready to manually label the peaks, and then I'm gonna put my cursor or my mouse on this peak, that peak, and I'm labeling each one. So as you can see, this goes from 0 to about 8. So this is called the downfield part of the spectrum to the left, and the upfield part is on the right side over here. So now the next part is what is called integration. So the integration determines the number of hydrogens in that peak, in the cluster of peaks. So if I click integration, I can set this arbitrarily by placing my mouse before and after the cluster of peaks. So this is called a triplet, and typically this area would have a stage 3, but again, this is arbitrary, so I'm going to do a reference to 3. That corresponds to stage 3. And then it now gets adjusted to 3. So this 3 corresponds to the number of H's in this triplet. So this is a triplet, quartet, a broad singlet. So now the 3 corresponding to that number in here in the integration would be the area under the peak, the area in this triplet. So the total area of these 3 peaks would be 3. Again, it's arbitrary. So if I now do integration again on this quartet, I'm going to place my mouse, I hold it, and then I drag it on the other side, and then that's going to be 1.98 or 2, because there really is no 1.98 protons, there are 2. So you round it off to the nearest whole number. So that's 3, because I set it to 3. So these peaks are coupled to each other, meaning they are neighbors. So that means this number would be 2. You round it off to 2. That's going to be stage 2 and stage 3. And now, if I have this broad singlet, I do again, integrate it. And now that's close, that's 1. And now that's 1. So that means that you have 1 hydrogen under this peak. You have 2 hydrogens in this quartet. You have 4 peaks, 1, 2, 3, 4. So if you cut this out, the total area under this quartet would be 2 hydrogens. This one, the area under the peak, you're measuring from here to here. This area would be 1 hydrogen. And again, this triplet would be 3 hydrogens. So 1 hydrogen, 2 hydrogens, 3 hydrogens. The label here are the chemical shifts. So 0.96 ppm, 1.11 ppm, 1.27 ppm, and so forth, up to 5. So this is the most downfield shifted peak, followed by this quartet, followed by the triplet. So again, this is in chemical shift frequency ppm. So that's it. So the next thing is you just print it out, and I will provide every student a copy, a hard copy of the unknowns or any sample for the experiment.